In 2016, there were 1,350,000 road fatalities. That means, on average, every 24 seconds, somebody died on the road. That's the equivalent of a commercial airliner falling out of the sky every hour of every day of the year. Up to 50 million people are injured or disabled every year in car accidents. And the National Highway Traffic Safety Administration did a study to understand what are the causes of these accidents. And they found that over 94% are a result of human error. The vision, the dream of autonomous vehicles is to remove the human from the loop and reduce these casualties by at least an order of magnitude. This is one of the big challenges of our generation. Good afternoon, everyone. My name is Ronen Slasky. I'm the head of technology in AWS Israel. And today, I'm going to give you a glimpse into the world of AV development. I'm joined on stage by Tal Babayev, VP of Mapping and Localization at Mobileye, and Yanor Baras, Cloud Development Manager at Mobileye, which is one of the most innovative companies in this space. Tal and Yanor are going to be telling us how Mobileye are using AWS for their AV development, how they achieve scale, some of the challenges they face, and the solutions that they've come up with. Tal will also be telling us about some of the new business models that have been born out of the quest for AV. Let's start by talking about AV development. So the components of an autonomous driving system are typically divided into three subsystems. We have the perception and the sensing systems. This is where the car needs to understand its environment. We have the decision-making systems, which is where the car needs to figure out where it wants to go. And finally, we have the execution systems, which actuates on that plan that the car has decided that it wants to go. An autonomous vehicle has many different sensors inside of it. It's got cameras, lidars, radars, and the car takes data from all of these sensors and it builds a 3D model of the world so that it can understand its environment. It then needs to place itself inside this environment, and we use HD maps for that purpose. These are high-precision maps with rich semantics, and this process is called localization. The car then needs to figure out where it wants to go and how it wants to navigate through the world. This process is called path planning. Finally, the car needs to use accelerating, braking, and steering commands in order to actuate on that plan. What you see here is a typical AV development workflow, whereby these AV companies have fleets of cars driving around with all of these sensors that we mentioned before. They collect lots of data. We then ingest that data and then pre-process that data. Some companies prefer to pre-process the data before ingesting, whereas other companies prefer to use the elastic compute in the cloud to do the pre-processing already in the cloud. After that, we need to label all this data, and then we build our models and we train the models. The next step is model simulation. Simulation is a very important component of the AV stack. Here, we take data collected from real-world driving and play back that data with our new models and algorithms and compare that against human-labeled ground truth data. Once that's complete, we then need to evaluate our models to see how they compared and ensure that we didn't add any regression. If we did, we then need to go back, tweak our models, train, simulate, and evaluate, and we iterate until we get it right. Once we're ready to deploy the model to the car, there are a number of things that we need to do to ensure that our models that until now have been running in high-performance compute environments can run in a compute-constricted environment. These are things such as quantization, pruning, and compression. Once we've done that, we then deploy it to the car, and the cycle starts from the beginning again. In our presentation today, we're going to dive into data ingestion. We're going to talk about model simulation, and we're going to talk also about HD mapping, which follows a very similar workflow to what you see here. If anybody's interested in hearing about model training or model deployment, one of Mobileye's machine learning engineers, Chaim Rand, gave a talk about this very topic, how Mobileye uses AWS SageMaker to run training jobs at scale on AWS. There'll be a link to that talk at the end of this at the end of the session. I highly recommend you check it out. So AV developers have many, many challenges, and I've only listed a few of them here. And we're not going to dive into every one of these use cases. I've left this primarily for reference. But the point that I wanted to make here is that doing AV development is all about doing things at scale. And to prove my point, let's focus on one specific use case. So we spoke about these fleets of cars that drive around collecting all this data. Each car can collect up to 100 terabytes of data per day. We typically have tens of vehicles, sometimes up to 100, 120 vehicles in our fleet. And if you do the math, that's hundreds of petabytes of data per fleet per year. This is a lot of data. And when dealing with data at these scale, at these volumes, there are many challenges. And for each one of these use cases that you see on the screen, there are a number of different AWS managed services that can handle the undifferentiated heavy lifting for you so that you can focus on your AV development. Here, I want to focus on one specific use case, data labeling. So all this data that is collected needs to be labeled. And AV companies typically hire hundreds or thousands of data annotators in order to label all this data. This is a very labor-intensive task. Amazon SageMaker Ground Truth is a service which uses machine learning-driven auto-labeling to reduce the labeling efforts by up to 70%. Amazon SageMaker Ground Truth can integrate with your own private human labeling workforce, or you can use Amazon Mechanical Turk in order to access human labelers via an API request. If anybody here has labeling requirements and hasn't tried out Amazon SageMaker Ground Truth, I highly recommend it. It's a really cool service. So we've spoken a little bit about the AV development workflow. We've spoken about some of the challenges. Now I want to dive into two reference architectures, one for data ingestion and the other for simulation. So on the left, we have our AV fleet. And on the right, we have the AWS region and the S3 bucket that we want to ingest our data into. In the middle, we have what I like to call our smart garages. These are basically garages or colo facilities where the cars are parked overnight. These garages are outfitted with multiple 10 gig direct connect connections to ensure that we have sufficient bandwidth between our garage and the region. Now, there are multiple approaches that we can take, and this all depends on where we want to do our data pre-processing. Some companies prefer to use the AWS cloud to do the pre-processing, and then thus they want to get the data into the cloud as fast as possible. What you see here is a serverless workflow for the data pre-processing. We're not going to dive into this right now because we're focusing on data ingestion. So here, data is typically logged in the cars via data loggers. We remove disks from the data loggers, and we mount them to data logger copy stations, which we've built inside the smart garage. And from there, we copy to S3. In order to ingest data into S3, we can either use the AWS SDK and build our own ingest mechanisms, or we can use AWS Data Sync, which will handle the parallelization for us to ensure that we fully utilize the bandwidth that we have allocated. For fleets that I like to call nomadic fleets, which are not in physical proximity of the garages, customers use Snowball Edge to ship the data physically to AWS, and then AWS are responsible for ingesting that data into your S3 bucket. For customers who want to do the data pre-processing in the garage, they typically build mini data centers in the garage. They then copy the data from the logger copy stations to the mini data center. They do the pre-processing and then ingest the data to S3. Let's talk about running simulations now. So there are two types of simulations that we're going to talk about. The first is resim, and here we're replaying actual data collected from real vehicles. The second is driving simulation, and these are computer-simulated driving scenarios. So on the top left, we have our developers and our data scientists who want to run their jobs, their models, and validate their algorithms. The key component here is AWS Batch. AWS Batch is a cloud-native job scheduler which handles the provisioning and scaling of resources. It allows you to create job queues to which you submit your jobs to, and then compute environments which will run your jobs. In this reference architecture, Batch is spawning spot compute environments to achieve maximum cost effectiveness. The artifacts for these jobs are typically stored in S3. But most resim or simulation applications require POSIX-compliant file systems in order to access the data. And so we use Amazon FSx for Lustre to serve as our high-performant file systems. Kinesis data streams is generally used by customers together with a cache database to keep track of simulations progress at the processing stage. Customers then build their own dashboards in order to visualize this data. At this point, I'd like to hand off to Tal Babayev to tell us how Mobileye are using AWS for their AV development. Thank you very much.
Thanks very much, Ronen. So I'm coming from Mobileye, and I would like to tell you a little about Mobileye. Mobileye is a company which was founded 20 years ago in order to reduce fatalities on roads based on adding computer vision to cars and adding safety. We are selling vehicles, or we are selling within vehicles functionality like autonomous emergency braking, lane centering, traffic sign recognition in vehicles which you can buy today. We have sold over 17 million vehicles last year, 50 million over lifetime. And we have been concentrating on adding safety via vision. Our normal processing now is coming into advanced driver assistance systems. This is what you can buy today. But it is only natural to take this technology and move it into autonomous vehicle driving as we are doing from today. The real issue is that if you think of building an autonomous car, you need to take into account that you need to react to humans. And humans are driving around you, and they are okay drivers. Yes, they are making a lot of accidents, but most of the time they drive, and you need to be much better. So you need to understand how you can reach the same failure level of humans, which is in terms of billions of hours. And this means that the validation is actually very, very hard. On top of that, you need to address the rare occasions in which the system would fail. It means that you have to look on large amount of data and find these scarce events, which is very, very hard to find. On top of that, not everything is available today. If Ronen suggested that HD mapping is critical for us to build an autonomous vehicle, the current technology which was used for building HD maps is actually very, very expensive, highly manual, does not work in scale, and actually something which we couldn't buy in order to use for our autonomous vehicle. And this is part of why we decided that we have to come with our own solution. So let's look now on how autonomous driving looks like. We have our car, we have our driver, he's doing nothing. We have cameras looking all around the vehicle. I'll show all the setup of them later on. And we have a map. This map is projected on the images. You can see the yellow lines looking on the edge of the road, the center line which define where vehicles should drive. And this map allows you to put the sensing information on top of it, like you see on the right top view. When looking on autonomous driving, Mobileye decided going on a very specific approach. We're going camera-centric. We have humans which are driving today. Maybe vision is good enough, so let's take it this way. And we would have something which works end-to-end based on vision. We understand that redundancy is critical, and then you can add a LiDAR or radar on top of vision in order to have a better redundant system, but you're not building the essence of the system around a LiDAR, which means that you can do everything faster and cheaper from today. When looking on driving between humans, we understood that we have to make sure that our car would never be liable for an accident. Otherwise, we would be blamed and you would not ever have a car on the road. So we formalized a mathematical model around who is responsible for an accident in the real world. We call it RSS. We comply with this RSS inside our driving policy, which means that we can drive between humans in a safe manner. You are welcome to read about RSS in our publications. And we understood that there is a need to add HD mapping to the technology. We said we would have to do it ourselves. Let's do it in a crowdsourcing manner, and I would talk about that in detail in the rest of the talk. A glimpse on how our autonomous vehicle look like. So we have cameras around the vehicle, 12 cameras to begin with. We start with 3 cameras looking forward in different resolution. One which is very wide, which reflects the front window of the driver. One which is a little more narrow, which reflects the main objects which we care about. And one which is very, very narrow to allow us to have a long foresight into the future. We have cameras looking to the side, just like the 2 side windows, and something which reflects the rear and side mirrors. So we have 360 sensing around our vehicle, and the same algorithms which detect vehicles in the front is also detecting objects and vehicles all around the car. On top of that, because vehicles today have parking cameras, we also use parking cameras for short-range detection. And this allows us to make sure that our car would not hit any other object around it. So once you think about these 12 cameras, some of them are going to be 8 megapixels, you understand that the validation effort and being able to run all this data is a huge problem at scale. And I would hand over to Yanor to talk about it and explain the challenges and the solutions.
Thanks, Dan. So hi, my name is Yanor Barros. I'm responsible for the development and migration of Mobileye's infrastructures to the cloud, including validation. So 18 months ago, we embarked in a journey with AWS to reach ultra-scale resimulation validation. I will try in the next 15 minutes or so to explain to you the main challenges we faced in this quest for scale and the solutions we have found. And we've created an AWS-based, cost-efficient processing system for hundreds of petabytes of data per month. And we're spinning 500,000 cores in parallel to do our validation on a daily basis, and we'll keep growing. So let's dive into that. So first of all, let's understand our workloads. Our main workload is resimulation. Years ago, my brother was working on sensing algorithms. So when he wanted to test them, he would hop on a Mobileye car and try them with different scenarios. But resimulation is different. Resimulation meaning running a real software on real recorded drivings. But the hardware, instead of being our Mobileye's highly optimized hardware, it is on vCPUs, commodity hardware. We are doing also data preparation for machine learning and analytics in scale, like, for example, analyzing the results of resimulations. This variety of workloads means that we have a lot of requirements, different requirements, memory, CPUs, even job duration. We have jobs that are taking 30 seconds and jobs that are taking many hours. So we must handle all of this. Our workloads are extremely dynamic, their frequency, their urgency, and the scale. A developer can run the resimulation on one recorded drive, or 1 million. Our system has to be fair, so we cannot starve any workload. We cannot say, okay, that's everything has to have some CPUs. And the system has to coexist. The AWS ultra-scale system has to coexist with our on-premises data center. So they have to data sync that has to be needed, has to happen, and they have to coexist to play well together. So now let's build together a system step by step. So as Ronen mentioned, we are collecting data from with our fleet, millions of driving. Each of these driving, we collect all the sensors of all the cars. That's terabytes of data. In Mobileye, we call these driving, we call them clips, as in video clips. By the way, one of these clips is especially dear to me because it features our autonomous vehicle doing an automatic emergency brake when a certain pedestrian, me, didn't look before crossing the road, and now I can live to tell and even present. So let's go back to our system. So we have a jobs API. It's GraphQL based, running on API gateway, which allows a developer to submit a resimulation job to AWS Batch, as Ronan explained. AWS Batch is handling jobs. It's a 300-level lecture, so I'm not going into all the details. I assume some level of knowledge. So when a developer would like to submit to try to test his vehicle detection algorithm, he's using the jobs API to submit the software to run, a list of clips, a list of drives to run on, and the result will be saved in a simulation result bucket, S3 bucket. So how is it implemented? We track our jobs with DynamoDB. It scales, it handles all the scale that we need. AWS Batch and Amazon ECS, they're integrated, so they are scheduling and managing the containerized jobs. Everything is Docker-based. And AWS Batch is using compute environment, which are AWS instances, containerized instances, and to execute the jobs. In Mobileye, we have special lambdas, we call them sizers, that are controlling the spot fleet, the compute environment, their capacity. So, and this we control it according to the need, the exact requirements we currently need. So spinning up or terminating them. Everything is based on spot instances with attached EBS storage. So basically, just a recap. It's containers, Dockers running software which is downloaded from S3, clips, a clip which is downloaded from S3 again to the EBS storage. The software is executed on the spot instance, and the results are uploaded to a result bucket. We use CloudWatch events to update our database from dashboards, alarms, etc. If we look at algorithmic validation, we want to understand the result of the resimulation. So it's very similar to resimulation, except that the input, instead of being clips, instead of being the drives, is the simulation results. And since it requires less CPU to process than the simulation itself, we can continue the work on our on-premises data center. Because any data that we'd like to sync back to our on-premise is sent to an SQS queue, like download request, and we have a system which reads from the SQS and downloads the results. And just to complete the picture, as Ronan explained, the data processing, the data collection is using exactly the same jobs API to do any processing of the raw recorded data or any enrichments we need. Okay, so now that you know how to build such a system, and you're perfectly welcome to try it at home, let's understand the challenges that we faced. Basically, there are 4 considerations to take into account that are conflicting many times, and the job of my team was to try to find solution for one aspect without having any heavy impact on the other aspects. So let's start with user experience. So the wait time. The developer does not want to wait a lot of time for his job to start. We understand that. And he wants also the system to be fair if he's running something with low priority. From cost efficiency point of view, we want to spin up cores only when they are needed. From robustness point of view, we may need to do retries, so we may need to retry to fetch the containers in case there are problems there, but this doesn't add a lot of overhead. But the main point is that the AWS batch, the component that we rely on, is FIFO, first in, first out, which doesn't give any good fairness or guarantee wait time. And the solution that we found for that is use relative fairness. We divided the jobs into clusters according to amount of clips they are working on. So if you're running your resimulation of 100 drives, it will be a different queue than if you're running on 1 million. And then it's first in, first out, but per cluster. Also, the light queue, which is almost an express queue, it's almost interactive work. So for that, we spin up also a small amount of EC2 spot instances ahead of time to save the time it takes to start the EC2 instance. And you can also use AWS batch priorities, but use it with care because make sure to not have any starvation. Second challenge from user experience is we said that we're syncing back results to our on-prem system, and as our scale started to grow and grow, our validators wanted to be faster and faster, so we kept adding a lot of servers. We like our customers happy. We're team players, and we reached scale, a very high scale of complaints from our IT department saying, what are you doing, guys? It's clogging completely all our storage. And so remember, the AWS scale must not overload your on-premises, your data center. The scale, the elasticity is completely different. The solution that we found for that is to, every time we need to download something, we write to an SQS queue, and then the on-premise data system is reading from the queue, and according to the resource availability and performance, it pacing the downloads, which solved completely the problem for us. Let's move to cost. If we are spinning up that many CPUs, what do we do? So our approach was simple. Use only spot instances. Our finance department was really happy. For us, it was more complex because with a 2 minutes notice, any instance you have can be taken from you. Even if you are doing retries, you cannot guarantee for 100% a success rate because every time it can be taken. Our solution for that was to minimize the amount of spot termination. And we do that by doing diversification. By diversification, I mean use as many instance types as possible. This is AWS best practices for using spots. The tricky part is that it conflicts with trying to optimize using the instance type to the exact job requirement, memory, CPU, and stuff like that, and which is also a saving factor. So you have to balance according to your workload to get to a point that you're happy with, to balance between these two factors, because otherwise there will be too much spot terminations. We also use AWS batch retries, and we implemented a smart retry mechanism, when to retry, how to retry, and stuff like that. Second cost is the EBS. We said that we download the software and download the clips. First, it worked very well. We started growing in scale, and our bill started to grow. And we had to find a solution for that. And what we've done is to use Goofies. It's a POSIX-ish file system, which allows us, instead of downloading to EBS, we're just mounting so that our application thinks it's a POSIX file system, but in fact, we're fetching only the data we need from S3, where the clips are. It's an open source written in a Go language, and we improved it a bit. It's read-ahead and allowed roughly sequential reads and not byte accurate that we needed. For us, it worked really well. We were able to reduce by 90% our usage of EBS. You can imagine the cost-saving factor in it. I have to say that it adds complexity to the system. So it's not do it only when you know what you're doing and play with it step by step. Second cost factor, third and last cost factor is utilization. You're paying for any running instance, so you want to maximize the CPU usage. For that, we are controlling the spot fleet ourselves, the capacity. And originally, we've done it because our diversification strategy was not supported by AWS batch. It is today, but it still allows us to get to a high utilization of above 90%. Scale. That's the coolest challenge. And I'm just going to give 2 examples and try to spare you the math. But let's take the challenge of jobs that are very short. So as any AWS service, they have limits, AWS batch and Amazon ECS also. And one of the limits is the maximum TPS, transaction per second, the maximum amount of jobs, the new jobs that can be handled any second. So let's take an example. Let's say you have 20. That's the maximum. So 20 new jobs. In a minute, it's 1,200 new jobs per minute. And let's say our jobs are only 5 minutes long. They are short jobs. So what will be the impact of that? You can see on the graph. It ramps up nicely, but then it reaches a plateau because the new jobs, the old jobs are already starting to finish, and it's exactly the same pace that the new ones are starting. So you get to a plateau, and you're stuck on the 6,000. So what our solution? To do job packing. Let's think of putting the jobs in pairs. So now you have jobs of 10 minutes, and you reach a plateau only after 10 minutes. And you're doubling your concurrency, your amount of parallel cores that you can run. And if you can do it with pair, you can do it also with packs of 25 jobs. And then you are going to reach a plateau, but only at 150,000 cores in parallel, which is much nicer. It will allow you to finish for 3 million jobs. It will allow you to finish it in less than 2 hours, what originally would take almost 2 days. Second example about scale, the jobs with a varying duration. A bit of a background. For scale, AWS batch use array jobs, up to 10,000 jobs each. The number, and also it has a number, it has a limitation on number of active jobs, the jobs that can be scheduled, that are being scheduled. So let's see how it works together. Let's say an example submits 30,000 jobs, which is in 3 arrays. All of them are active, they are all running. But after a while, most of them are finishing, except 4 which are taking longer time. What's the problem with that? That all the 30,000 jobs are still considered active because there's no single array which can be freed. And it's a big problem when you get to scale or ultra scale because you may reach the AWS batch limit, and it means that new jobs cannot be processed, which has a very bad influence on the system. The solution for that is to reduce the size of the arrays, but do it with consulting AWS because you do not want to impact their performance on the scheduling. And the second thing, which is nicer even, is if you can sort the jobs by the estimated duration. If you have any way to say, okay, that these jobs are going to take longer, I put them in the same array. And what happens is that only one array continued to be taken, and the rest can be freed using the same example as before. This had a dramatic effect on our scaling. So basically, using these techniques, we're able to reach hundreds of petabytes of processing per month, spin up 500,000 cores. That's in 1 hour, you have 70 years of compute, very nice success rates, and in cost-efficient solution. For the ones who can read the graph, that's the amount of cores that we have in parallel in a 2 weeks timeline. So what's interesting is not only that we reach the 500,000, but also that you can see that it drops significantly, even to 0 when there's no need. And this elasticity exactly what our Mobileye wanted from us to have as infrastructure, that when something is needed, you have it, but otherwise we don't want to pay. Taking one step back, so from our customer point of view, all these changes and moving to the cloud allow us to move our cycle duration from 1 month to a few hours. Our product quality went up because we're able to run on more clips, more drives. The development is much more agile because if a developer wants a CPU, he has it, and it's cost efficient. And now to Tal, we'll explain about mapping.
Okay. So we're going to talk about autonomous vehicles. And the real question is, why does autonomous vehicles need a map? Actually, we have maps today. We use them every day.
Your mic's not on.
The mic's not on. Mic on? Thank you. Okay, so why are we needing a map? Today you have Google Maps, for example. You've driven Google Maps, and when it told you to turn right and you continued straight, it took it 100 meters before understanding that you took the wrong path, which means that it's not relevant for autonomous driving. Think about the last time you drove in Europe. Can you turn left on green? Can you turn right on red? You have a lot of understanding which is coming from the semantic of the environment, which is very, very local, and it can be represented well in a map. And if you think about this autonomous vehicle, which you saw before, what's going on behind this hill? Is there a junction there? Can vehicle comes from the right, from the left? There's an information which you can have sensing, and sensing could be great, but there is always beyond sensing. On top of that, when we think about vehicles and pedestrians which we see, we need to understand if we should care about them. Is this vehicle in my path? Is this pedestrian on the road or on the sidewalk? Having a map allows you to improve the sensing on top of allowing the vehicle to know where it has to actually drive in such scenarios. So what's the alternative? The common approach is taking a LiDAR, a very expensive one, put it on a vehicle or 100 vehicles, drive around, collect the data, create a cloud of points, connect them together, build a 3D model, and define a map, and then add, probably manually, all the semantics. And this is becoming very, very expensive, both because of the equipment and second, the labor, the manual labor, and does not reflect reality well, because if this road change, I need to send another sensing vehicle to that location and create the map, and this does not work well because 10% of the road changes every year. Now, on top of that, you have millions of kilometers of road in every continent, which means that you have to have something which is cost efficient. So we said, let's take a different approach. Let's look on our cameras. We have cameras today which are actually detecting road-relevant elements every day. We're detecting lane marks. We're detecting traffic signs. We're detecting the road edge. If we had every vehicle driving around and telling us what it saw, we could take these drives together, combine them, understand what's common between all those drives, and model the world in a way that we would actually be able to reflect the reality in a good manner, and also be able to localize ourselves in a centimeter accuracy, which is what we need in order to be able to drive according to the map only and not seeing the lane marks. So we call this concept REM, Road Experience Management. And the concept of REM is very simple. It's like 1, 2, 3, 4, 5. You start by harvesting. You ask from every vehicle to tell you where it drove and what it saw. And we're not sending any images outside. We're sending very, very compact information, 10 kilobytes of data per kilometer, which means that if you have a vehicle driving full year, it would collect 200 megabytes of data. This is equivalent to 60 songs, very, very tiny. Now, this data must be anonymized and must be such that it does not violate your privacy, because otherwise nobody is going to let us to collect that. And we are also encrypting it and sending it to the cloud. Now, when we're getting to the cloud, we can look on data. Some data came from different positions in the world, but some came from the same road. So whenever we have enough data from the same road, we can create an aggregation. We can look on many, many drives, see that they would fit well on top of each other. We call this step alignment, and then model it to create a road book. A road book would be our version of map, telling the vehicle where it can drive, what it sees while it's driving. Again, because we started with semantic information, this roadbook is also going to be very tiny. We're talking about a tile, 1 by 1 kilometer, around 200 kilobytes. So it's something that you can send over 3G. You don't have to wait for 5G. And then at the end, there would be a localization step. The vehicle would sense the landmarks which he sees, poles, traffic signs, lane side, road edges, would be able to localize where he is on the map, identify his position within centimeters, and then utilize the map for any decisions that he needs to do. So this got us to a nice situation because we have very big advantages. We have many, many vehicles driving around. We are selling millions of vehicles every year, which means that we have good crowd for crowdsourcing. This crowd could give us accurate maps to the date. So whenever a change happens in the world, we would have vehicles driving there collecting data for us, which means that we have short time to reflect reality. On top of that, we said manual could not be part of the equation. We have to do it fully automatic in the cloud, and then we can have something which is cost efficient, short in time. The map, change to map time would be smaller, up to minutes or seconds. The last decision that we made as a design decision was to have very, very small footprints, send very tiny amount of data. This allows us to send data from millions of cars, because otherwise the communication cost would have been significant. And we are not sending any images or video, which means that we're not providing any privacy violation to the people which are driving in the car or around it, which is GDPR nicely. The nice thing, as we see it, is that we have a market from day one. When we create maps, we can sell them for Mobileye customers, which would use them for enhanced normal driving. You can have a better car with better lane centering or better activity even before autonomous driving would arrive, which means that we have customers today. We don't have to wait for the autonomous revolution. And the last is that we have a smart camera, smart agent in the vehicle, which means that we can collect on top of the static data also dynamic data and understand if there are hazards on the road or how is a driving looks like, collect insights, and use them for smart cities and other applications. When we take this huge problem, it allows many challenges. The ingestion is coming from millions of cars. You have to do it in a flexible manner. Not all of them are driving all the time. You have to have elasticity in the solutions there. We have to be cost efficient and scalable. There would be tens of millions of cars. There would be billions of kilometers of road segments. You need to store all the data. You need to process it in an efficient manner. The compute is not going to be identical. You have to have some stages in which you run Spark with 50,000 cores, and some days you are running very low compute. And on top of that, you want to have some live streaming to identify change detection in the world and be able to know where you have to create maps and where not. We need to do it in a global scale, and everything must be secure, and AWS has been the right solution for us. So we're going to deep dive into the ingestion pipeline alone, from data coming from the vehicle until we can use it. So we're starting from the vehicle. It transmits its data. We start with some kind of network load balancer in order to address the fact that millions of cars can transmit in parallel. Then we're moving it to authentication cluster, which would check the encryption, the signature, would check that the right entity is willing to send the data. And then we have authenticated data moving into our REST RAM. REST RAM is a point in which we define the recipe of what to do with the data, where it should be indexed, how it should be indexed, where it should be saved in S3. And then before sending it to a Kafka queue, we added another component called ingester, which allows us to have a buffer there so that we can take down the Kafka if we want and never lose steps. From the Kafka, we pull the data using a secure machine. We move it to a temporary storage, which triggers a Lambda, which would put the data into S3 and also index the data into Elasticsearch for future use. The indexing could be looking on information, geographical information, and also we would be having other information for us. If we want, we can also add a Spark emulation, which would either work in streaming directly from the Kafka or work in batch, pulling data from the Elasticsearch and then going to the S3 bucket to collect the raw data and create a map. We have been working a lot with Lambda, and we're running very complicated algorithmic code, which was really not what Lambda was on their mind when they thought about it. So we're both running long compute, and also we have huge executables. We understood that we have to put this executable on the /temp file system of the Lambda on the container in order to be able to squeeze into the limitation on code size. We know that there are limits for how much time you can run a Lambda, and in some cases we want to rerun the Lambda because the code changed, and we use Spark in order to reiterate that and not have to build an alternative mechanism for such running. And we have developed a custom error handler for our step function in order to address errors and log the failures using the CloudWatch. We recommend for you to log everything. We've been using CloudWatch log very successfully for that. We recommend the insights in the CloudWatch logs for better search capabilities. And we recommend to index in Elasticsearch all the REST APIs, request and response, so that you can debug efficiently this kind of serverless step. This is how our harvesting look like. So you see a video, but the video is what's happening in the reality. Everything which is collected is the points which are collected on the video, and what's sent is what you see on the right, if you can see it. So very sparse information. The poles, the lane marks, the reflectors, the signs, and that's it, 10 kilobytes per kilometer. And this data we have today all around the globe. We have around 200,000 vehicles today transmitting. We will have around 2 million by the end of next year. And you can see very well, nice footprint from South America and Australia, but you can see how much Europe is yellow and how much the center of population in the US is also yellow. Already today with these tiny numbers, we are still in the very start step of getting data. And this allows us already today to create maps very nicely. Just to give you a feel, today we are collecting 5 million kilometers a day. We in accumulated, collected more than 3 times the distance between Earth to the Sun in the last year. And next year is going to be 10 times more than what we collected this year. One of the hardest problems that we have in map creation is the ability to align different drives. We get GPS position. It could be wrong by meters. And we have to put them in a centimeter accuracy, one on top of each other, in order to model the map. You can see here's the result of such alignment. Each drive gave one purple point. And you can see how well they look when they're sitting on the lane mark. It means that our alignment was very, very well. This allows us to create a map. And what we are going to see here is a map. On the left side, we are projecting it based on the localization on the video. On the right side, you can see it on a top view. And once you see, you can see that the purple lines reflect the lane marks, and they sit on the lane mark with a pixel accuracy. This means that this map is very, very accurate. You can see how well the signs is sitting on the signs in the reality. It means that this map allows you to have good localization and gives the vehicle all the information it needs for autonomous driving. And we've been doing that a lot. We're doing it on a weekly basis on major cities in Europe. For example, Berlin. You can see the center circle in Berlin. You can see Paris. On the left, the coverage of Paris. Everywhere we have a yellow line, it means that the map was created there successfully. And on the right, you can see the fine details of the map. The green lines are lane marks. The red points are traffic signs. The blue points are poles. Same for VW headquarters, which are one of our customers. We have map around their base location, And here, very close, San Francisco, from a handful of BMW cars, we created a nice map around the center of the city. So we are today in a stage we are doing production in scale. We are creating maps of the entire world. We took an example to run the Japanese highway system. We produced the entire Japanese highway system by less than 24 hours compute on the cloud. And we plan to have a fresh Europe map from Q1, meaning that whenever a road changes in the world, it would be reflected, the change in the map within a day. When looking on our data, we started from ADAS, Advanced Driver Assistance System, and AV, collecting lane marks and road marking and road edges and so on. And we understood that there is a huge potential to add to our vocabulary other objects which has interest to various companies. So we talked with utility companies which care about where there are manholes and drainage and telco boxes and electricity cabinets, so we are collecting that for them. We have demand for detecting surface waters and pedals, so we're detecting those now and reporting back such. We're looking on road quality to identify cracks and surface quality for companies which are doing maintenance, and we are collecting that in the near future. And the goal at the end is to be an intelligent agent which detects every road event and every road element which is around there. This is a visualization of the problem on the left side. When looking on 10 kilometers of road in London, there are more than 5,000 objects there. If you would have sent a fleet of measured people which would stick them and identify where this location, it would take them weeks. We can do it as a byproduct of driving. And on the right, you can see a video of driving in Japan in which these objects are detected as byproduct of our camera and reported back all the poles and traffic signs and reflectors and road arrows and zebra crosses, et cetera, et cetera. This is another visualization of the assets which we are collecting today. There is a huge importance if this is a street light or wired pole, so we added that activity for companies which care. There's a question of construction monitoring, so we added that functionality. So we are now creating data which is relevant for any company which is looking for asset management, for city operations, for city planning, for public transportation. Think about how much the value equals to Uber if I tell them where many, many people are standing and looking for another vehicle to pick them up. Fleet management system, all the data is high refresh rate, no human in the loop, it's very high accurate, it's relevant for any functionalities they want. I wanted to give you a feel about how dense we can collect data, so we asked to look on where stop signs exist, and you have stop sign on every corner in such area near JFK, and you can see how fast the population of all of the stop lines were created by our cars driving around. Today, we're collecting data either from vehicles that you buy with camera installed in them, or we can have a retrofit system, which is an IoT device with a cellular link and a GPS that you can put on every vehicle. And we have an OTA functionality that we can put new software on it and increase this data which we are harvesting by changing our functionality or our models. Another visual example of a city. This is Los Angeles. This gives you how fast drives or roads are over 24 hours. The more blue the line, the faster the road is. You can see how red the center of the city is. And this is a great information for route planning or for road planning at all. When we look on our data, we made sure that our data is accessible. So if you think about this traffic light, which was detected by a camera, we had many cameras driving around. We created a map. We can output this data on the relevant platform for city managers, which is ESRI, so they can take it and look at it in the same GIS information systems that they are ready or useful to look at in every day. We have a few more minutes, so let's dive into New York City. We had a fleet of cars driving in New York City. We looked what we can find around it. So we have all kind of information looking around, where vehicles are speeding, what's the cycling path, pedestrians on highway, construction, jaywalking. I'm not going to show all of them. Let's look on some. So let's look on this road. This road is a 45 miles per hour road. We see vehicles driving there around 60 miles per hour. Do we care? Not so much. But if we look on the same area or another area, and we see that there are vehicles speeding on one hand, we have a lot of pedestrians running around there, and we have reported accidents from the history of the city, which means that this is actually a risk factor, a place in which you are not willing to live unattended. You want to understand that this is an area which is unsafe and correct it. And this is something that we can give on top of just looking on spread of accidents, which doesn't give you this information. Another type of information is bicycles. We looked on bicycle passes in New York City, and this dashed lines is where the municipality put bicycle passes. And on top of that, we reflected a heat map which showing where we saw bicyclists. So on the left, you can see that we have actually nice bicycle lanes which are populated by bicyclists, which is great. But in the center, you can see that the bicycle lane starts there, which is great. This doesn't work. But when it continues and the bike lane moved one street to the right, nobody uses it because the bicycles actually prefer to take the straight and not take a right and a left. So you can see that there are some bicycle lanes which are never used while vehicles are driving in other area. And there are areas in which you have many, many bicyclists driving and you don't have a bicycle lane. So this can give you an information of where to put your infrastructure and where to improve and where to invest the right time. Here we took something different. We started to think, can we have a risk score for each road? When looking on data which is coming from our camera, where do I see a lot of pedestrians? Where do I see a lot of bicyclists? Where do I see vehicles which are doing harsh braking? Where do I see vehicles which are doing cornering? The driver is moving the windscreen, the wheel very, very fast. And where do I get pedestrian warning or pre-collision warning from our safety system? And I can take all of that and combine that into an information and understand which roads are safer and which roads are less safe. And if I have this information, I can actually do smarter routing. You can drive the fastest route, or you can wait another half a second, half a minute, and drive on a safer route. Are you willing to do that? This is information which actually gives true value to the driver. OK. To finish my lecture, I would give you a view of HD mapping in real life by driving an autonomous vehicle. So you have here the worst of the worst. In nighttime, in rain, reflective road. You don't see the lane marks, but you have a camera and a map. And when you do the localization based on objects which you do see, these traffic signs, these poles, you can reflect the map and be able to give the vehicle the position of the lane marks, even if the vehicle itself cannot see the lane marks. So I can give more availability to the autonomous vehicle, and then I can show the true redundancy which I'm giving when the camera does not see the lane marks very, very well. So this is an autonomous driving in Jerusalem, driving around using our camera in nighttime. So to conclude, we, as a vision camera company, understand and believe that camera is the best sensor for us for crowdsourcing for mapping. It's affordable. It has a lot of data coming out and very, very high precision. We were able to take this crowd of cameras for creating mapping, and we see high demand for such mapping with the fact that we can give this very, very fast update for the maps for various applications. We have been using AWS for creation of these maps. This allows us to regionalize HD mapping and do it in a cost-effective manner. And we're ready today to map all the world, which is why we think that AV can be later on deployed all the world. As Ronen said before, we have the related breakout for deep learning, which was this morning, and you can find it in the video in the future. And I'd like to thank you. If you want to ask questions, we would be in a meet and greet functionality in level 3 area in Ironwood foyer. Thank you very much.